Hello, good day everyone. First of all, apologies for the mic quality in case it's not quite the best. But yes, thank you for waiting. This is the last lecture for our semester, and it will be on combustion engine cycles. Now, is this anything different than what you've covered before in NSI 14 and ME 70? Actually, no, not much. To make things a little easier, because I know most of you are having final exams soon, including ours. This last topic will just be very light. We're just going to connect back from going over the fuel side of things, the reaction side. We're just going to circle back towards the machine aspect of combustion engineering, which is the engine itself. Most of the engines that will be focusing on this topic, or at least for this topic in this semester, will be mostly internal combustion engines. If you are curious about other kinds of engines, you can approach us, me, Ma'am Precious, Ma'am Rhea, and other faculty if you're curious about it. There are a lot of interesting things that is going on with the non-standard cycles that um, are usually not covered in your two-digit courses. So all of the cycles that we'll be covering are mostly what you've covered before. So this will be the auto, diesel, and dual or mixed or limited pressure cycle. And I've actually been trying to think of ways to spice this up. Um, I'll try to cycle it back to the previous lessons, but it won't be much. It's more of an explainer on what you've been doing for two subjects, most of all. So we're just going to review some things because even though this is something that you've already taken and presumably learned for two subjects straight before reaching this point, and we need to cover some things again because talking about the cycles for internal combustion engines without the context is, or rather without the terminologies, is very confusing. So first of all, we have to remember that the three cycles that we're going to cover today are for piston cylinder engines. So for piston cylinder engines, there are common features in terms of their construction. So first of all, they are closed chamber combustion units. So you need a way to get the air and fuel in. So for either diesel or gasoline engines, you both have intake and exhaust valves to take care of that. And of course, um, the piston itself, it does not push to zero volume. Of course, even though it kind of rises at a certain point, there is always still a little bit of volume left because it's impossible to compress air to nothing. So in a sense, you have what we call the clearance volume or the minimum volume of your piston chamber, or rather cylinder chamber, I mean. And the position of the piston that is associated with the clearance volume is what we call the top dead center. So if we have a top dead center, we also have the bottom dead center. So this is the lowest position of the piston. And the distance between these two dead center positions, this is what we call the stroke of your engine. And to complete it, we also have the bore or the diameter of your cylinder. So the bore is the diameter. In case you're curious why it's called the bore, I believe it's because the cylinder is finished through, or rather, it achieves its final internal diameter through what we call the boring process. So essentially, you drill a hole into a solid block, and then to expand that hole, you bore. That's it. I have to check, but I believe that's what boring means in the manufacturing context. You're trying to expand the hole to a specific diameter. So that's why it's called the bore. Next, now if you pattern the pressure against the volume for a single cycle and you plot that on a pressure specific volume diagram, you get a cycle, a thermodynamic cycle. So this graphical area here, this is actually the network of your system. So we are in the pressure volume diagram. So any area that you form here is equivalent to a network. Now, if you transfer over to the temperature entropy diagram, any area that you enclose there is equivalent to the heat, that the difference between the heat taken in and the heat taken out of the system during a single cycle. So here, what you'd see here is that, oh, of course, this is an Otto cycle. So this is not a diesel cycle. So you have two volumes, and to make things to communicate certain aspects of the engine, engine manufacturers decided on naming a particular ratio that we all know. This is the compression ratio, or for single terms, it's denoted by the symbol R. So R compression ratio is equal to the maximum volume over the minimum volume, which is the clearance volume. Now, all right, so we have your network, you have this area enclosed. Now, there is another parameter for denoting engine performance. You can obtain this by taking this area here, this entire area here, and then converting it into a rectangular space. So if you convert that, you turn this into a rectangular space, you get you're still bounded by the clearance volume, the max volume, but now you have this even pressure. This even pressure is what we call the mean effective pressure, or the MEP. So essentially, you're approximating the entire network of your system as an isobaric work. And the pressure during that quote unquote isobaric process is the MEP. So it is fictitious, but it kind of helps you understand how much horsepower or how much power your engine is outputting. The higher the MEP, essentially, the more powerful your engine is. All right. So now, what I showed before was a model of an engine cycle, but if you look at the top right, you will see an approximation of what the actual cycle might look like. So the question siguro for some of you would be, how do we know that this is actually what the PV diagram of a single engine cycle looks like? So this kind of cycle was actually figured out long before we had sensors. Long before engineers used engine indicators or planimeters. They attached a sinusoidally rotating tissue roll, quote unquote, a tissue roll, and and they connected a certain marker, um, something that will draw on the piece of paper as it rotates counterclockwise, then clockwise, and counterclockwise again. And from there, they are able, through the planimeter, to figure out the plot of the pressure versus the volume for a single cycle. So in the olden days, they actually used this to check on the engine, uh, in particular to see if something is going wrong. I believe this was something that they did for ships or very large combustion engines. So the planimeter was their way of checking if the engine is all right or if it's actually doing what it's supposed to do. Nowadays, though, we are actually using transducers or sensors that convert physical stimuli into electrical signals. We use those to instead plot the engine cycle for us. So it's a little more complicated, but it's a little more complicated, but it's still expensive to set up. So during the olden days, they wanted to figure out, okay, so we can see the pressure volume plot of our engine cycle. So like, how do we improve this? So, like, how do we figure out ways that will effectively increase the output and increase the efficiency of our machine? So instead of just working with the actual plot, they tried to model the actual cycle using much simpler series of processes. And that's where the auto, diesel, and dual cycle arose. So within these cycles, there are variations. There are several kinds of models. The simplest of which is done using the cold air standard. So I hope the cold air standard is still familiar with you. This essentially assumes that for the entire cycle, the only thing that you have is air. There's no fuel, just air. And its properties does not deviate from room temperature or 25 degrees Celsius. So the next step from that is modeling the engine with air still, air throughout, but the thermal fluid properties, the specific heats, they start to change with temperature and pressure. So that is the variable specific heat model for engine cycles. And as you go along, you also have what we call fuel air cycles, where half of the cycle is assumed to be air still, but right after or during rather the combustion process, you treat the fluid as if it's now combustion products. So as you go along, there are multiple pathways to approximating the accurate cycle. But for this part of the subject, we will only be focusing on the cold air standard. If we're going to encounter variable specific heat, we will provide the appropriate tables or ask you to print the appropriate tables. So this chart is a comparison. You have three models here. You have the cold air standard in orange. You have the variable specific heats in dark blue, and the fuel air cycle in green. So as you get a little more accurate, some of the area is actually lost, and that is a consequence of getting closer to the real deal. But of course, there is no real deal unless you actually have experimental data on the fuel cycle. For this case, I wasn't able to obtain any experimental data for this. So you can kind of ignore for now the fuel air cycle. We won't cover that. We will be only focusing on the cold air standard. So since we're going there, we have to remember some 25 degrees Celsius properties of air, particularly the CP, the specific heat at constant pressure, the specific heat at constant volume, the gas constant of air, and the specific heat ratios. So these are very important. You may carry this up to your board exam review. Uh, the this series of numbers, they don't change as much unless the examiners actually change the reference, but I think they will not deviate from this. So in a sense, it is useful to memorize these four properties for air at 25 degrees Celsius. So, all right. The rest of the slides will just be a quick rundown of what you already know. So, first of all, we have the auto cycle. We assume again that the fluid inside the inside the piston cylinder chamber is just air, and it has constant thermofluid properties. And the cycle is broken down to four parts. You have two constant volume heat exchanges, and you have two isentropic um, volume changes, or rather work, essentially, whether that's work in addition or work work done or work done by the system or work done on the system. Sorry, process 1 to 2, that is the compression. Process 2 to 3, that is the constant volume heat addition. Process 3 to 4, that is the isentropic expansion or the power stroke, and process 4 to 1, that is the heat rejection. So given this, we do have some conveniences because we're using the cold air standard. In particular, since you have two processes that are isentropic, it is useful to remember the three-way relationship between the temperatures, the volumes, and the pressures between the initial state and the final state. So these three relationships, they are consistent for isentropic processes. This is useful to memorize in case you get lost. I probably will not put this in a formula sheet. I will expect you to remember this. So here you go. You have a temperature ratio of final over initial that is equal to the initial volume over the final raised to K minus 1. K being the specific heat ratio of your fluid. So this ratio of volumes is actually equivalent to the compression ratio, or R. Now this also has an equivalent pressure ratio side, that is K raised to K minus 1 over K. So this is consistent for process 1 to 2 and process 3 to 4. You just have to be consistent on the placement of the end and final states. So for the temperature ratio, when it transitions to the volume, you swap uh, the the placement of the states, and then when you go from volume to pressure, you swap the states again. That's how I remembered it. Or you can make up your own mnemonic for it, essentially. So for the cold air standard processes, you have a fixed set of formulas for the work and the heat added and the heat rejected. So for both work processes, the compression and expansion, it is polytropic or isentropic. So there is already an established equation for these. So they are all small letters, specific work and specific heat. So you don't have masses attached. So what you'd see with the isentropic work processes, they are in the gas constant times delta temperature form. There is also the pressure volume form, if you can recall. You can also use that. For the heat addition, just recall that we are assuming that the combustion takes place in a constant volume process. So your entire heat addition formula will be CV, constant volume specific heat times the delta T. Now, to get the efficiency, you just take the network and then divide it by the heat addition. Or you can go through a derivation process and you'll end up with this expression for the thermal efficiency, which is 1 minus 1 over compression ratio raised to K minus 1. So this is all from Insight 14. I hope you still remember what these are. I will not derive them anymore. Um, Hoping for the best that you still remember. So, all right. That is the Otto cycle. Now, for the diesel cycle, instead of a constant volume heat addition, we're going to assume that the heat addition happens over a constant pressure. So, as you're adding heat, um, what's essentially happening is that the fluid is expanding as you're adding heat. So, there is a work component that is happening during the heat addition. So again, you still have two isentropic processes here associated with work. When processes happen, you're assuming that there's no heat that is being exchanged during the process. So you have two isentropic work processes. You have one isochoric or same constant volume heat rejection, and you have one constant pressure heat addition that is happening. So you can still carry over the isentropic relations for both the compression and the isentropic expansion, but because you have limited pressure, or rather constant pressure heat addition now, there is now a specific work from process from state 2 to 3. And in order to express that, we have to take note of what we call the cutoff ratio, or the ratio between the volume of state 3 to the volume of state 2. So here in our specific heat and specific work processes, we have heat addition from state 2 to 3 that is now equal to Cp, or constant pressure specific heat times delta T. So this is different from the Otto cycle. And you have work associated with that. So since this is an isobaric or constant pressure process, so it's just P times delta V. Now there is also isentropic expansion. So of course, you still have this. Now, I didn't do this for the Otto cycle. I didn't put a second row of isentropic equations because you can essentially swap the you can just change the numbers and essentially not much will change. However, since you adjusted the since your initial and final volumes are no longer the same, what you'd notice here is that the simplification for the volume ratio, it's not just going to devolve back into the compression ratio raised to k minus 1. So for the expansion process, your ratio of volumes is actually equivalent to the cutoff ratio over the compression ratio. So this is an important thing to note between diesel cycles. So it's a little more complicated than that. Again, the thermal efficiency is just the network over the heat addition. But of course, uh, you can simplify the expression, and you will end up with this. Well, it is simplified technically, but it's a little more complicated than the Otto cycle. This is the thermal efficiency of the diesel cycle under cold air standard. So it looks like the Otto cycle efficiency, but the second term is multiplied to this behemoth here that consists of a ratio of cutoff ratios. Is there an easier way? Um, you can just focus on deriving the network and then the heat addition, so you don't have to remember this. But this is a useful shortcut if in case you're having struggles with deriving the work for the three processes. So right, those are the two simple cycles, but of course, we are open to being a little more accurate than simple constant volume and simple constant pressure heat addition. So the dual cycle actually assumes that there is both a constant volume portion of heat addition and you also have a constant pressure portion of heat addition. So most of the time we assume that this is 50-50. So 50% of the heat addition happens at constant volume, 50% at constant pressure. But this ratio can change. But if there is no mention of the split between the processes, you can just assume that it's 50-50. So the dual cycle has actually a lot of names. Sometimes it's called the mixed cycle. When we were learning the dual cycle, our instructors called it the limited pressure cycle because it's partially constant pressure only, but it's uh, not quite fully constant pressure. I believe one of your professors actually called it the Trinkler cycle. There is another name. There's another name that uses a proper noun, but I actually didn't check what it was. So, all right. The difference here is that your total heat addition will consist of both a constant volume and a constant pressure heat process. And this is something that you have to take note of, especially when you are solving problems. Now, if you recall, the Otto cycle, oh, sorry, the Otto cycle is supposed to approximate gasoline engines. The diesel cycle is supposed to approximate diesel engines. So, all right. So, what does the dual cycle approximate? Actually, you can get a clue from one of the other names of the diesel cycle. So it's called the limited pressure cycle, and that refers to the constant pressure cycle not being fully the entire process. So the dual cycle is actually an approximation, not for not for gasoline engines, but for diesel engines actually. So it's kind of weird, but yeah. There's actually an engine that operates on the dual cycle, like it completely operates on that principle, but I will not present that here in during the recording. It's all right. It's okay. Now that we've covered briefly the what you've learned in NSI 14 and ME 70, perhaps now we can cover the whys. Like, why is it that for gasoline engines we assume that it undergoes the Otto cycle? Or why is it for the diesel cycle we assume that it's for diesel engines? So it has something to do with the characteristic of the fuel that is being used. So although gasoline and diesel might be so for most of you probably have never actually had a bottle of gasoline and a bottle of diesel be sat in front of you in one place. So there is actually a fundamental difference between gasoline and diesel. So gasoline is very volatile. So there's a difference. When you say volatile, it readily becomes vapor that mixes with the air. So when you're trying to combust a fuel, the first part of the fuel that combusts is actually the vapor part of your fuel. So it's not the solid part, it's not the liquid part, it's actually the gaseous part or the vaporized part that instantly ignites. And gasoline is really, really ready to ignite. And that's why it's very dangerous to store gasoline indoors because if the container of the gasoline has a leak, if you and if you accidentally put it next to a source of flame or source of hot temperatures, it might spontaneously combust. So it's volatile, and because it's volatile, it easily combusts, and it's actually easier to completely combust the fuel. So what you see here is, although it's not that obvious, there is a video. I will attach it with the recording as well. So there's a video of a sample of gasoline, a sample of diesel. The researcher tries to set the gasoline on fire. Of course, you can see in the picture it's really on fire. But for the diesel, um, it takes a while. So it doesn't burn instantly, even if there's an open flame right next to it. So when it comes to diesel, you have to think of diesel as kind of like an oil. It has an oil-ish consistency. It doesn't vaporize, or it's not as volatile as gasoline. Um, you have to actually mist it or turn it into a spray before you can do any useful combustion to it. So if you can see here in the top picture, um, all the fuels presented are in liquid form. And although in the combustion chamber, the fuel is essentially gasified, or no, not gasified, it's atomized and mixed with the air. Diesel in its liquid state will not combust easily. So you have to mist it so that it can mix well with the air, and it actually burns much slower than gasoline. So here in the bottom picture, this is actually still gasoline versus diesel. So this flame from a gasoline, and the right one is a flame from diesel. What you notice is that for the gasoline, the flame is bluer. So when you have a blue flame, it indicates that there's not a lot of soot in the combustion products. That means that the combustion is more complete. While in diesel, since the combustion is a little slow, not all of the reactants become fully combusted. So there's a little bit of incomplete combustion. So you end up with soot or non-combustible products. So because gasoline is actually ready to ignite, it's just ready to go. You can kind of assume that once you trigger the combustion, it's just poof, it's fully combusted. So that's where we get the assumption that the combustion happens within the clearance volume, within the constant volume of that minimal space. So the approximation comes from there actually. So since gasoline combusts really quickly, it's kind of like instantaneous. Like, okay, kaboom. So there's no volume changes. The heat addition is just done instantly. So that's why we model the Otto cycle for the gasoline engine. Now for the diesel engine, the fire, the flame is actually slower to burn. So when you ignite diesel and air, the piston actually, when the combustion does not complete before the piston starts to move. So essentially, the combustion reactants, they are fully combusted, but the piston has already moved essentially. So because the diesel air mixture burns slower, the combustion completes itself very late. So essentially, you can think of it as, oh, it's so slow. The piston has already started to move. Before you have finished adding the heat in, the piston has already moved. You can think of it that way. So that's why it's actually a better approximation to just assume that the heat addition is constant at constant pressure. And sometimes you can use the dual cycle to just assume some part of the heat addition happened at a constant volume, but the process of heat addition will not complete itself without the piston actually moving. So yeah, that's, I'm not sure if I explained it well, but that is the gist of why auto is assigned to gasoline and diesel is assigned to diesel. So in terms of thermal efficiencies, we're going to compare the thermal efficiencies of the auto and diesel cycles with respect to increasing compression ratios. So if we look at the thermal efficiency equation of auto cycle, you can see that the efficiency rises with the compression ratio, albeit there will be diminishing returns as you increase it. The same is true for diesel cycles, but what we notice is that as you increase the cutoff ratio, the efficiency actually drops. So higher compression ratios actually help with the efficiency, but to help with the efficiency, it's better to just lower the cutoff ratio. So for diesel cycle, you can think of it this way. The more that you can the more that the diesel cycle can approach the auto cycle in terms of being instantaneous or being fast, the more efficient it is. So yeah, actually. So you can think of the cutoff ratio as, it's kind of like the efficiency of the burn or the efficiency of the combustion. If you have a really small cutoff ratio, that means that the fuel actually burns more completely. And if you have a big cutoff ratio, essentially the combustion stopped and the piston actually moved way, way down already. So yeah, weird connections, right? So yeah. Again, just to review, the auto cycle engines or gasoline engines, they usually put their compression ratios between 8 and 11. While for diesel cycles, they start from 12 and usually end at 24. So the compression ratios of either engines are marked out here in orange. Now, there are limitations to chasing efficiency. The more obvious one is for the auto cycle. So even though the auto cycle is actually ano, it will improve its efficiency if you increase the compression ratio. There is a hard limit. Once you go beyond 11, there is a potential to trigger engine knocking, or what we call spontaneous combustion or auto ignition. What you want out of a gasoline engine and in engines in general is that the combustion must be controlled. You have to perfectly control the timing of the flame and the propagation of the flame. If you increase your compression ratio further, there's a potential for the gasoline to reach its auto ignition temperature, meaning the temperature at which it will just combust itself. It will become out of control. It will become spontaneous, and that is something that's very terrible for the longevity of your engine. You actually get engine knock, which might eat away at your parts. So this is a hard limit because of the characteristic of the fuel and the properties of the materials. Now for the diesel cycle, uh you don't actually suffer from auto ignition. In fact, auto ignition is what you want to happen in the diesel cycle. You don't have a spark plug there. Um the only hard limit for the diesel cycle is, of course, the reality of the construction, the size of the engine. You might be limited in the space that you want to put it in, or perhaps you're limited by the materials that you can use. So those are the hard limits for the diesel cycle and the gasoline engine. Now, if if the three cycles were to take on the same amount of heat, like let's say 800 kilojoules per kilogram, uh, their network would be as follows. So the Otto cycle be will actually extract the most work out of the three. That'll be followed by the dual cycle and then the diesel. And because the net work of the Otto cycle is higher for the same amount of heat, it's actually more thermally efficient than the other two. Now, this is actually balanced out by the fact that diesel actually is denser in terms of available energy per volume. So, a full tank of diesel has more energy than a full tank of gasoline. So, even though the auto cycle is more efficient, there is a lot more power that is locked inside the diesel fuel. So usually they are more, I know, you have more heat available to extract. So since you have more heat, even though you have a lesser efficiency, you can actually get more power out of diesel. So that's why diesel is used for heavy set equipment, because diesel as a fuel has more punch than gasoline. Even though gasoline is ready to burn, diesel just packs a lot more power. So now, how do we improve our engines outside of the cycle? Can we actually augment our engines to essentially produce more power or become more efficient? So one way of doing this actually increasing the mass flow inside our cycle. So you can actually increase the fuel flow, but most of the time, the majority of the fluid that is flowing into your cycle is actually air. So if you can push more air into the cylinder per cycle, that would actually increase the punch of your engine. So in engineering terms, we call this the forced induction. So there are two ways to increase the mass airflow. One of them is not as common anymore. The other one is actually very well used up to this day. So the first one is the supercharger. I believe your generation is not as well versed in cars now. So I think most of you haven't seen a supercharger. So this is what a supercharger actually looks like. Inside, there are two. There is a twin screw compressor. They are kind of meshed in place, and the supercharger gets its rotation from the powertrain. from the crankshaft itself of the engine. So as the crankshaft turns, the supercharger turns, and the supercharger, being a screw compressor, actually drives air into the cylinder, and that is actually more air than what it would normally draw. So the supercharger is not that common anymore. The reason why is that the supercharger is powered by the crankshaft. So even though the supercharger is providing more air and causing the engine to expend more power or produce more power, part of that power is actually being taken away in order to power the supercharger. So it's kind of like a parasitic power increase. So even though you plug this component in, it's stealing power in order for the engine to make power. So that's the reason why it's not as popular now. The other one does not do that. This is where we go to the turbocharger. I mean, so if the supercharger is a screw compressor, the turbocharger is essentially a centrifugal compressor, and it is powered by the centrifugal turbine at the back here. So this shiny silver side is the compressor. This slightly matte steel is the turbine side. So the turbocharger gets its power from the exhaust flow. The exhaust actually flows into the turbine side, and it drives the shaft that also drives the compressor. What's neat about this is that the turbocharger, it's not coupled to the powertrain. So it is not stealing power from the engine, but instead using a waste product of the combustion process in order to suck in more air for your engine. And that is why it's become the more common kind of forced induction method rather than the supercharger. So these two components, they actually alter the characteristic of the cycle models, but we will not be talking about those right now. So for some examples, just a really quick one. So again, we are tackling cold air standard cycles. No shenanigans from variable specific heat, whatnot. So all right, let's go through this. So example 7 to 1. An auto engine intakes air at 95 kilopascals and 27 degrees Celsius, and it accepts 800 kilojoules per kilogram of heat every cycle and has a compression ratio of 8. So using the cold air standard, you have to find number 1, the maximum temperature in Kelvin, number 2, the thermal efficiency, and number 3, the mean effective pressure. So with thermodynamic cycles, if you don't know where to start, just start by drawing the cycle. So if you draw the cycle, you can identify, oh, there are 4 states. So you can just draw a table of the states and the properties that you know are associated with each state. So here I have a table, states 1, 2, 3, 4, and you have the associated properties, pressure, temperature, specific volume, and other associated properties. So right now we only know a lot about state 1, but we do know about the compression ratio, which will help us find properties of state 2, and the heat addition, which can help us find out about properties in state 3. So all right, let's start. Uh, the first uh, the first property that is being asked of us is the maximum air temperature. So when is the temperature of the air at maximum? Of course, it's right after the heat addition process. So that would be state 3. Now, where can we get the temperature at state 3? So if you look at our given, we have given heat addition. So since this is an Otto cycle, your heat addition is equal to CV delta T. All right, so CV is actually known. That's 0.718. That's T3. We actually know QA. How do we know T2? So T2 is actually the end state of an isentropic compression process from state 1. And since this is an isentropic process, we can actually pull out one of those k minus 1, k minus 1 over k relationships. Since we have state 1, we can actually compute for state 2. So this is one of the pressure, volume, temperature ratios in isentropic processes. So our K is 1.4 for air. And since we have T1 and we have R, we can easily compute for temperature 2. So temperature 2 is around 689 Kelvin. And since we have QA 800, we can just plug this in and solve for the temperature at state 3. And that is 1800 Kelvin. So the trick here is remembering um, which process is associated with which states. So processes happen between states. Um, this table where I put others, this is actually wrong. R equals 8 should be would better be placed between 1 and 2 rather than 1. And QA would be better placed between 2 and 3 rather than 2. So take note, the processes actually happen between states, not in the states. So, all right. Next, we have thermal efficiency. So for thermal efficiency, you can go at it in two ways. You can try to solve for the network, which would mean that you have to complete the states so that you can compute for the isentropic compression and the isentropic expansion. So that is a valid way of solving this problem. But you also have another out. You can just pull out the thermal efficiency formula for the Otto cycle. And for in terms of Otto cycle, or rather in terms of efficiency, the Otto cycle isn't that hard to memorize. So since it only requires the compression ratio, this one is easy. This is 56% efficiency. It's all right. Next, we have the mean effective pressure. So the mean effective pressure, right now I didn't flash the shortcut formula. So we have no choice here but to fill out the states, essentially. So all right. Mean effective pressure is equal to network over the difference in volume. So first and foremost, we have to fill out the states. So this is actually easy. So for example, we have state 1. We are given pressure and temperature. And you have to recall that under cold air standard, we are assuming ideal gas behavior. So that means we can actually compute for the specific volume of this state. So if you use P small v is equal to R times T, you can solve for small v. And that will be 0.9063. And for state 2, that is going from maximum to minimum. So you'll just have to divide the volume of state 1 by the compression ratio. And that is 0.1133 meter cube per kilogram. And now you just have to copy these values to state 3 and state 4. You can use the PV diagram to actually keep track of which value belongs to which. So it makes it easy. Next, since we've completed the volumes, we go now to temperature because we only have one left, T4. So T4 would actually be derived from an isentropic ideal gas property ratio, specifically this one. You can use this to actually derive for T4. So when you do that, you'll get 785 Kelvin. Why did we get the temperature instead of focusing on the pressure? That is because in network, you have isentropic compression and isentropic expansion, and there is a version of those formulas that only uses delta T times R. So you only have to solve for one property instead of two. So if you do that for the isentropic compression, just like here, and the isentropic expansion from 3 to 4, you will be able to solve for the network. And network is 451 kilojoules per kilogram. If you plug this in here, we have Vmax zero point 0.9 and Vmin zero point 0.1. You will get a MEP of 469 kilopascals. So, right. Next, we have another example. This is a diesel engine and it outputs 140 kilowatts per cycle. So it has a compression ratio of 20 and a cutoff ratio of 1.25. Find number one, the peak pressure in kilopascals and the rate of heat addition in kilowatts. Use the cold air standard. Intake conditions are 90 kilopascals and 57 degrees Celsius. So this is a diesel cycle. So if it's a cycle, the easiest way is to just draw it and then plot the state properties. So this is what we know so far. We know a lot about state 1 but not much about the rest. However, we are given the compression ratio and the cutoff ratio. So let's do something about the first task, the peak pressure. So if you look at our graph, fortunately the vertical axis is pressure. So we just have to look at where the peak pressure is. So what you notice is that the peak pressure is shared between states 2 and 3. So okay, so P3 is equal to P2. And what we know about state 2 is associated with the final state after isentropic compression. So now we can pull out isentropic property ratios. So P2 over P1 has a relationship between V1 and V2. So it's good to memorize these things so that you can just plod along without having to um, go through a lot of derivation processes. So it's just this. You can actually simplify this. You can just take out k minus 1 since it is a shared exponent. And then you can multiply k so that what you'd end up with is r raised to k, and p2 over p1 is essentially exponentless. And you'd end up with a pressure of 5.9, no, 6 megapascals. It's 6 megapascals. So it's pretty high, pretty high. Next, we will solve for the heat addition. So instead of solving for the heat addition straight up, we will actually go through the thermal efficiency first. Why? Because the thermal efficiency has a fraction or a formula that involves both the network and the heat addition. And the thing is, we have an expression for the network, which is 140 kilowatts. If we can know the thermal efficiency, we can solve for the heat addition immediately. So you can actually go through all of the states in order to solve for the network. But if you are a savant and you memorize the formula for the thermal efficiency of the diesel cycle, this will be quite easy. So you have all you need for this formula. So the cutoff ratio, you have the specific heat ratios, you have the cutoff ratio. You can just substitute and then solve for the efficiency without going through the states. The thermal efficiency here is 68%, and plugging that in, you'll just have to divide 140 by 0.68. You will get a heat addition of 204.7 kilowatts. So is it that easy? Will it be that easy in the exam? I'm not sure, but that's pretty much it. So what about the dual cycle? I think you'll be able to handle that. One of our references, particularly Sengel and Sontag, has sample problems hidden at the end of the chapter. Not hidden, but put in the end of the chapter. If you want help with those problems, I think you know where to find help for that. So is that it? Yes, that is it. Thank you so much for listening, and good luck with your exams, and have a um, very productive series of Hell Weeks. And I hope you stay hydrated, stay well rested, and please make sure that you are doing well and whatnot. So again, thank you very much.